Professor, you're muted.
Today we study the Newton's method for the solution of system of nonlinear equations. Here is a system of n equations and n unknowns. Very, very general. Each equation is nonlinear. To derive the Newton's method for the solution of a system of equations, take a review about Newton's theorem in k variables. I want to expand this function. I want to expand this function at the point x1, x2, and xk. The formula is summation I from 0 to n 1 over I factorial times h1 partial derivative with respect to x1 plus h2 partial derivative with respect to x2 and so on. HK partial derivative with respect to xk, then power I. To compute this derivative, you need to expand the power. And then function x1, x2, xk, then plus error term. Where the error term is 1 over, let me see, oh, here is n, so this is n plus 1 factorial, and then times h1 partial x1, h2 partial x2, hk partial xk, then the power is n plus 1. Take derivative on the function k. After computing this derivative, then plug in the point, okay. Then plug in the point x1 plus data x1, x2 plus data x2, xk plus data hk. After computing this derivative, then plot this point in the result. Where data, we don't know what is data, but we are sure data between 0 and 1. Between 0 and 1 data. This is the Taylor's theorem in k variables. Now, today, we need this expansion, Taylor's theorem, to derive Newton's method for a system of equations. First topic, okay. In this topic, let's consider a simple case. A system of two equations in two unknowns. Then in the second topic, we generalize the result to a general system, okay? Now, topic 1. We want to solve this system of equations. Two equations in two unknowns. Okay. Suppose the root, let me denote the root by arrow, okay. This is a R1, R2. The root is arrow, suppose, okay. And then suppose this point x tilde arrow x1 tilde x2 tilde be an approximation to the root arrow. Okay, now let me introduce the difference between x tilde and the root. Okay, now R1 minus x1 tilde, R2 minus x2 tilde be h1, h2. Yeah, the difference is h. Now from here we can see that move x1 tilde to the left side, then R1 is x1 plus h1, and R2 is x2 plus h2. Now, in the following, okay, we want to estimate h. We want to estimate h. After we get h, then plug in h here to get a better approximation, better than x1 tilde, x2 tilde. How to estimate h1, h2? Use Taylor's theorem in two variables. By assumption, R1, R2, this point is a root of this system. So if R1, R2 should be 0. F2, R1, R2 should be 0, right? Should be 0. Okay, now let me plug in these two equations. R1 is x1 tilde plus h. So F1 x1 tilde plus h1 F2 I miss R2. R2 is x2 tilde plus h2. This is R1 tilde plus h1, R2 tilde plus h2. Okay, now I expand this function f. By Taylor's theorem, I use the first two terms, then drop the error term. Okay, wait. Let me don't drop the error term first. Okay, expand this function at x1 tilde plus h, x2 tilde plus h by Taylor's formula. Then we have then plus h1 partial f1 partial x1. This partial derivative is evaluated at x1 tilde, x2 tilde. Then plus x2 partial f1 partial x2. Then plus error term. Error term should be E2. Yeah, should be E2. Okay. Do the same with F2 at this point. Expand it, then we get F2 x1 tilde x2 tilde plus h1 partial f2 x1 x2 partial f2 x2, then plus error term. Of course, this E2 and this E2 different. How about let me put a tilde, okay? Okay, now I drop the error term, then this equation becomes approximation. And I drop this error term, this equation becomes approximation. Let me continue on the new page. Okay, then we have 0 roughly is equal to f1 x1 tilde x2 tilde plus h1 partial f1 partial x1 plus h2 f1 partial x2. And the second equation is f2 x1 1 partial 2 partial x2. This is a linear system. Linear system. The unknowns are h1 and h2. Now, let me form this matrix. Form this matrix. J is a Jacobian matrix. Jacobian matrix. Yeah, let me form this matrix. The 1-1 entry is a partial f1 partial x1. 1-2 entry is this. Then partial f1 partial x2. Then this is a partial f2 x1 f2 x2. Of course, after we compute the derivatives, plug in the point. Which point? This point. x1 tilde, x2 tilde. Okay. All right. Then this linear system becomes. Let me move this term and this term to the left-hand side. Then the linear system becomes Jacobian matrix. Okay. Unknown h1, x2. Right-hand side roughly is negative f1 x1 tilde x2 tilde f2 x1 tilde x2 tilde. Okay, now solve this linear system. Move Jacobian to the right side. Then h1, h2. What is h1, h2? The exact difference between R1 and x1 tilde, R2 and x2 tilde. Okay. Now roughly h1, x2 roughly is equal to this. F1, x1, x2. Yeah. Yeah. So therefore, plug in this approximation in these two equations. Then we have R1, R2 is equal to x1 tilde, x2 tilde plus h1, x2. Now, x1, x2 is estimated by this vector, So roughly, this is equal. Roughly is x1 tilde, x2 tilde minus Jacobian inverse. Sorry, inverse, because I moved Jacobian matrix to the right side. So inverse F2 x1 x2 tilde. Yeah. Okay. We believe, okay, usually, okay, this new vector is closer to the root arrow than the original estimate x1 tilde, x2 tilde. Okay, now we define the Newton iteration as follows. Okay, let me call x1 tilde, x2 tilde be sk, x1k, x2k. Yeah, let me see the location. Oh, here. Okay. Let me call x1k, x2k be the x1 tilde, x2 tilde here. Then minus Jacobian times function value at x1k, x2k, f2, x1k, x2k. And this new vector, I call it x1 k plus 1, x2 k plus 2, k plus 1. Yeah. Then this equation is Newton's method for the solution of this system of nonlinear equations. After the second topic, I will show you one example, okay, about this vector form Newton iteration. Yeah, this is for a system of two equations. Now, second topic. How about the general system of nonlinear equations? Very similar. The difference is we use Taylor's expansion in k variables. Now, second topic, general system of nonlinear equations. Yeah. Actually, this is a very, very general. Now the formula is topic 2. Topic 2. Okay, we want to solve a system of n equations in n unknowns. 1, 2, n. Let me introduce some notations first. Okay, I let x below the vector of the n unknowns. And h, this vector, the h1, h2, hn. The function, vector function, okay, this function, the value is a vector, not a number. And also, independent variable is a vector. Yeah, this vector, x1, x2 to xn. Yeah. To denote the functions on the left side of this system, f1, x1, x2, xn, f2, x1, x2, xn, and fn, x1, x2, xn. Now, further, let me define this is a vector value function, not scalar value. The vector value function take derivative with respect to a vector variable. Derivative. The derivative of vector value function with respect to a vector. I define the derivative to be this matrix. Parcel F, F1, the first row. 1 entry. Now 1 to entry, parcel F1 with respect to x2, and so on. Parcel F1, 1, not n. Parcel F1 with respect to xn. The second row for function F2. Parcel F2, x1. Parcel F2, x2. F2, xn, and so on. It is a n by n matrix. So the bottom row is parcel Fn, parcel x1, parcel Fn, parcel x2, parcel Fn, parcel xn. Yeah. Derivative of a scalar value function with respect to a scalar variable. The result is a scalar function. Is a scalar function. Now, the derivative of a vector value function with respect to a vector, the result is a matrix. This matrix is called Jacobian matrix. Jacobian matrix usually is denoted. We denote this matrix usually by J. Okay, by J. Okay. All right. Now, with these notations, I can introduce Newton method for solving this system. The method is Newton's iteration. Is okay. X, this is a vector, and iteration k plus 1 is equal to xk, then plus hk. Hk, by using hk, we want to improve the accuracy of xk. Then what is hk? Yeah, here. Xk k minus, very similar to this two variable case. Okay, yeah, this is a xk plus 1, xk, then minus Jacobian inverse times this vector, very similar. It is okay, Jacobian inverse, then times the vector value function evaluate at x k. Jacobian is derivative minus derivative of the vector value function with respect to the vector x derivative. After we compute this derivative, plug-in xk in x. So actually, this is a take derivative, then plug in xk in x. Then take inverse. This is a matrix. Take inverse. Then times f at xk. Yeah. This equation is called Newton's method for a general system of nonlinear equations. Compared to the scalar value case, okay. Review, okay. When we solve a scalar value equation, the function value is scalar x, independent variable is scalar. The Newton's formula, the Newton's iteration is this: xk plus 1 is equal to xk, then minus f xk over derivative at xk, right? This is a formula we learned in the previous section. But I can write this quotient as xk minus f derivative xk, then inverse times f xk. So compare the scalar case with the vector value case. Actually, they're the same in structure, okay? Same in structure. So Newton's method for system of equations, the formula is easy to remember, very easy to remember. Actually, they are exactly the same in structure. Okay, now let me show you one example, okay, about how powerful Newton's method, how powerful this equation is in the solution of a system of equations. Take a look at one example. Okay, here. Example. Consider this system of three equations in three unknowns. x1, x2, x3 square plus 1. x1, x2, x3 plus x2 square is equal to x1 square plus 2. The third equation is e to x1 plus x2, x3 is equal to e x2 plus 3. How to find the solution of these equations? The formula is here. Formula is here. Yeah, here. Formula is here. Formula is here. Now, let me determine the vector value function first. Solution. The vector value function is f1, x1, x2, x3, f2, x1, x2, x3, f3, x1, x2, x3. S move all the terms on the right side to the left side. What is F1? F1 is x1, x2. Now move these two terms to the left. Minus x3 square minus 1. F2, I move x1 square and 2 to the left side. x1, x2, x3 plus x2 square minus x1 square minus 2. And do the same for the third equation. Move ex2 plus 3 to the left hand side. Minus ex2 minus 3 to the left hand side. Let me call this system, give a name, say 1. Then 1 is f arrow x arrow is equal to 0. Arrow, the 0 not a scalar but a vector. Okay. To use Newton's method, we need to compute derivative. Now, take derivative on function f with respect to the vector x. By definition, it is this matrix. Partial f1, x1, partial f1, partial x2. Second row for f2. Third row for f3. A 3 partial x3. Partial f1, partial x1. This is f1. Whole x2, x3. Fix it. Consider them constant. Then take derivative with respect to x1. Then we get x2. Then partial f1, partial x2. Take derivative with respect to x2. Then we get x1. Okay. Then the one free entry is negative 2 x3. Partial f2, partial x1. This is f2. Take derivative with respect to x1, then we get x2, x3 minus 2x1. Yeah, here x1, x3 plus 2x2, x1, x2, then e x1 negative e x2 1. Okay, now we have the derivative. We have the function f. Okay, now we need initial guess about the root. Initial guess is okay. Now I start Newton's iteration with this initial guess. I start with 1, 1, 1. Okay, 1, 1, 1. Start with this point 1, 1, 1. Then let me make a table. Let me make a table. K, the number of iteration. X1, the first entry. Second entry, x2, x3. Okay. Initially, when k is 1, x1, x2, x3 is 1, 1, 1. Okay. Now, first iteration. Yeah, Newton's method. Yeah. After we compute the derivative, plug in x0 in the derivative, then compute the inverse of the matrix, then multiply by this vector. Okay. After the first iteration, then we get 2.18932. X2 is a 1.59847. 1.39390. After the 2 iteration, we get 1.72822. Now run Newton's method several iterations. Let me skip the detail. Okay, the last iteration is 6. Run Newton's method 6 iteration, then we will get a very good approximation to the root. 1.77767. 1.2396. 1.23747. The result in the 6th iteration actually is quite good. How to know the result is quite good? Evaluate the function value at this point. The function value at this x1, at this x2, x3, very small. It is negative 1.55775 times 10 to negative 7. Quite good. Negative 5.067029 times 10 to negative 7. 2.8 2299 times 10 to the negative 7. So if we are happy about this small function value, then we consider this and this as the root of this system of three equations. Yeah. So power method, Newton's method actually is very powerful. The convergence is order 2. But the drawback is you need to pick initial guess about the root very close to the root that you want to find. One drawback. The second drawback is you need to compute derivative. Usually, derivative in practice not available. In practice, we usually suppose we have a finite set of function values. Those function values are data points, okay? Data collect from experiments, okay? In practice, usually we don't have a formula like this, okay? Yeah, we have formula in this example. We usually don't have formula for function f. So let alone to find derivative of the function. No formula, how can you find derivative of the function? So in practice, okay, what you can assume is just assume a finite set of function values. This is a topic 2. Now the third topic, secant method. Secant. This is from section 3, right? From section 3, yes. Secant method. Secant method, this method we want to improve, to overcome some drawbacks in Newton's method. Okay. Secant method consider the solution of a single equation, okay, not a system of equations. Consider the solution of a single function is scalar value. Variable is scalar variable. Okay, consider this equation. Now, Newton's method. Newton's method is sk plus 1 is equal to sk minus f sk derivative. A big drawback about this method is this method requires derivative. Now, how to draw derivative? There are many ways to draw derivative, to replace derivative. There are many ways. Say, let me show you 2 examples. The first example is called Stephenson iteration. This iteration reads sk plus 1 is sk, then minus f sk times f sk. Of course, this is a f sk square. Then over f sk plus function value at xk. Then, yeah, okay, f of xk plus function value at xk. Yeah, compute xk plus f sk. Then get some number. Then evaluate the function at that number, minus f xk. Yeah. So this part is roughly is 1 over f derivative at xk. Yeah. So Stephenson replace derivative by this part, But you know, I don't know why he replaced 1 over f derivative by this part. What is the rationale behind? Maybe complicated. Now the second approach, much easier. Okay. Recall that derivative is a limit. Which limit? This limit, right? Okay. Now, roughly, I can approximate this limit by this quotient. Function value at x. Function value at xk minus 1 in practice should be available. Okay. Function value at some points should be available in practice. Okay. We can get them through experiments. Replace this x by xk minus 1. Yeah. Okay, now I plug in this quotient in derivative. Now I get a new method. Okay, this is number 1. I don't know how Stephenson, why he replaced 1 over the derivative by this part. I don't know. But the second method much easier to understand. Okay. Xk minus f xk. Now replace derivative by this quotient. Okay. Now, and then call this new number as xk plus 1. Yeah. This replacement result in secant method. Okay. Now let me simplify this quotient. Okay. Simplify it. Okay. Then I get let me see. Xk plus 1 is equal to xk. Then minus, I move xk minus 1, xk minus 1 minus xk to the top. Okay, then f xk times xk minus 1 minus xk and over f k minus 1 f xk. Yeah. This is one formula for secant method. A second formula is xk minus 1 minus f xk minus 1 xk minus xk minus 1. Here f xk minus f xk minus 1. If you sit down and use a pen and a paper, it is easy to verify that this part, this expression, and this expression, actually, they are equal. No difference. Yeah. Either of these two formulas is called secant method. Now, About the detail of secant method, let me tell you the detail in the next class. Now I stop here for today's class.